Uh, Today we will solve the problem 2.12 and 2.13 of Griffith 4th edition, Introduction to Electrodynamics. The first problem 2.12 is use Gauss law to find the electric field inside a uniformly charged sphere. Charge density is rho. Compare your answer to problem 2.8. So I have taken a sphere of radius capital R, uh, for which the electric charge density is rho, and I am considering a Gaussian surface inside this sphere of radius small r. So the charge is uniformly distributed. So charge inside this sphere of radius small r, we have to find that is equal to charge enclosed by this Gaussian sphere. So from according to the Gauss theorem, in the integral form of Gauss theorem, surface integral E dot dA is equal to Q enclosed over epsilon naught. Now the charge enclosed, the ratio between charge enclosed to the total charge is equal to the ratio between their volume. That is the ratio of volume 4 by 3 pi r cube, small r cube, over 4 by 3 pi capital R cube. So 4 by 3 will get cancelled. 4 by 3 and pi will get cancelled. So you will get this ratio is R small r cube over capital R cube. So this Q enclosed, charge enclosed is a small r cube over capital R cube multiplied by this total charge. I brought this to the right hand side. Now E dot A, that is electric field over the area A, is equal to 1 over epsilon naught. Remember that this is area integration. 1 over epsilon naught, this Q enclosed, which is equal to R small r cube over capital R cube multiplied by Q total. E dot A is equal to 1 over epsilon naught capital small r cube over capital R cube Q total. Here now you bring this A is here, A is equal to 4 pi r square, small r square. Now this r squared and the r cube will get cancelled. This will become simply r. So this can be written as you bring 4 pi to the right hand side. E is equal to 1 over 4 pi epsilon naught. Here you have r divided by r cube q total. The total charge is the total volume of the sphere multiplied by the rho. Rho is the charge per unit volume. Then if you multiply it by the volume, you will get total charge. So this total charge, which I have shown in green color, is 4 by 3 pi r capital cube, pi capital R cube into rho. Now this 4 and 4 will get cancelled. This 4 and this pi will get cancelled. So in the similarly this RQ also will get cancelled. So finally you have in the numerator rho multiplied by R, and in the denominator you have 3 and epsilon naught, of course r cat along the direction r cat. This is the charge electric field inside the sphere, which is exactly same as that of problem 2.8 as mentioned in this problem. Then we will move on to next problem. Now we will solve the problem 2.13. The problem is find the electric field at a distance s from an infinitely long straight wire which carries a uniform line of charge lambda. compare with the equation 2.9. Now, this is the long straight wire which has infinite length. We are taking a Gaussian surface in the cylindrical form. The radius of this cylinder is, yes, I will use different color. Radius of this cylinder is S, and I am taking a length, this cylinder length is L. So now we have to use the Gauss law to find the electric field. So integral form of the Gauss law is integral over the surface E dot dA is equal to Q enclosed, charge enclosed by the surface divided by epsilon naught. So this is the Gauss theorem in integral form. Now the E dot TA is, if you integrate, you will get total area. This total area of the cylinder is 2 pi s is the circumference, and L 2 pi s circumference multiplied by L gives you the area. Then the charge enclosed. Here lambda is charge per unit length. So naturally charge for this entire length is lambda times L. Now the L will get cancelled on both sides. This L and L will get cancelled. Then you bring this 2 pi s to the right hand side. So here you have only lambda in the numerator divided by 2 pi epsilon naught, it is s. So s scatters, that is along the, this is unit vector along the direction of s. So this equation is exactly, this electric field is exactly equal to the equation 2.9 of the Griffith. So thank you very much for watching my video and supporting me continuously. Thank you very much.